Okay, so for this last video, we're going to do example 4 and 5. For this example, we're going to draw the picture first. We could also determine if it's continuous or not, or if there's just continuities if we did those 3 rules that has to be satisfied. That's more work. I think drawing it will be quicker. Okay, so for our first function, this can be rewritten as 4 over x minus 1, which means we have an asymptote at y equals -1, and a vertical asymptote at x equals 0. So I'm just going to draw this approximately. It's going to make maybe look something like this, and then we're going to have a hole where we stop, where x is equal to 2. And then we'll continue on, and then we're going to get a point 2, 2. And then lastly, we have x over 2. We're going to rise 1 and then go over 2. And again, rise 1 and go over 2. So you're going to have a linear graph that looks like that. So this is approximately what f of x looks like. Is this function continuous? You're going to say no, because we have a jump discontinuity at x equals 2. If not, where are the discontinuities? Well, we have one here at x equals 0, because that's an infinite discontinuity. And then we have another one here, which is a displaced point in a jump discontinuity. Okay, so x equals 0 is an infinite discontinuity. And we also have one at x equals 2. This part here is a displaced point. And because we have this displaced point, this can be moved to either one of these, and then it would turn into just a jump discontinuity. So we just kind of answered B and C here. If any discontinuities are removable, we write the function to remove them. So it's just as I was saying, you can remove a discontinuity if you fill in some of these holes here. So let's say if we filled in this hole, then we need a point at 2, 1. So I'm going to write that one first. So we're going to continue with the same type of graph. We're going to fill this hole here with y equals 1, x equals 2. So then we just have, instead of having a displaced point, we're going to just remove one of our discontinuities. You could also have a different one here, where we just change our domain to include it for this one. So we're going to include this one. So these are two different ways you can remove a discontinuities. Then our last example, example 5, we are given the function, but we're also missing a constant here. And we can solve for that constant if we make the function continuous. Okay, so we're going to satisfy those 3 things. We need the left-hand limit as x approaches 2 from the left. We need this to equal to the right-hand limit of f of x, which is equal to f of 2. So if this is satisfied, then we know the function is continuous at x equals 2. So f of x, when we're approaching it from the left side, is going to be 2 over x. And then once we evaluate this limit, is going to be 2 over 2, which is 1. So that's your, we're just going to call this L. We're going to call the right-hand element R. So this is going to be for x squared plus x plus c. And this is going to be equal to 2 squared plus 2 plus c, which is 4 plus 2 plus c, and that's 6 plus c. And lastly, I'm going to calculate f of 2. And f of 2 is going to be 2 over x. And in this case, my x is 2. So f of 2 is 1. In order for this function to be continuous, all of these need to be satisfied. So if I want to solve for c, 6 plus c has to be equal to 1 because the right-hand limit and the left-hand limit have to be the same. So we have 6 plus c is equal to 1. Solving for c, I'm going to move the 6 to the other side, which is 1 minus 6. So c is negative 5. And that answer is A. For B, given this value of c, will the function be continuous for all real numbers? F of x would not be continuous at x equals 0. Because if we look at 2 over x, we can't have a 0 in the denominator. So that means we're going to have a discontinuity there. So f of 0 does not exist. Now the last page for our lesson on continuity, I want you to try the following questions. So just hit pause, try those 2 questions, and then I'm going to show you the solutions after. Okay, so these are the solutions to those 2 questions. I've already written them down. For the first one, we are given the square root of 25 minus x squared. And then g is going to be the piecewise function that contains f of x and also the line x plus 7. We want to show if g is continuous at x equals negative 3 or not. So you're going to need to show the left-hand limit is equal to the right-hand limit, which is also equal to g of 3. So we've done each of those things. I labeled them as 1, 2, 3. Just to find the 2 different limits, and then to find, sorry, it's supposed to be g of negative 3. And then that's all. They are all equal to each other, so then g is continuous at x equals negative 3. And then for the next part of the question, you're given a different piecewise function. We want to show which intervals is continuous. And the only problem point would be when we have this 1 over x, it could be just continuous at x equals 0 because we have 0 in the denominator. So we want to show if f of x is continuous at x equals 0 or not. We find the right-hand limit and exists at 0. And then you try to find the left-hand limit, but then we get negative infinity. So since our left-hand limit and right-hand limit are not the same, our overall limit does not exist. So therefore, f is discontinuous at x equals 0. But if we want to actually find where it's continuous, it's going to be continuous everywhere except for when x is 0. So it'll be continuous from negative infinity to 0 and then 0 to infinity. And that's all for this continuity lesson. Please check your homework section in the OneNote because I've left a worksheet there for you to try.